So I'd like to talk about the FLUTe sequence of high-resolution hydrologic measurements. I use the term sequence because there's a series of measurements that are particularly useful for site characterization. The topics that I'd like to cover are a blank liner to seal the borehole against cross-contamination, the NAPL FLUTe cover on the blank liner to map the distribution of NAPLs and the dissolve phase. The FACT actually measures the dissolve phase. The FLUTe transmissivity profile to map the conductive features in the formation in great detail. The reverse head profile to map the head distribution in the formation. And the water FLUTe and the shallow water FLUTe systems to monitor groundwater quality and the head histories. The blank liner installation is very simple. The liner arrives at the site on the reel, inside out. We slide the top of the liner over the top of the casing and clamp it. We push the liner down inside of the casing, and then we add water. And the weight or pressure of the water, especially the excess head above the water level in the formation, is what drives the liner down the borehole. And this animation shows you how the liner propagates down the borehole as we add water. As the liner propagates, it also pushes the water into the formation. And what's very nice about this procedure is that you can reverse it. So if we pull up on the liner, the water flows into the borehole until we're out of the borehole. So the first question is, well, how well does this liner seal the borehole? Because the first point was the liner seals the borehole to prevent cross-connection. This is a snapshot of a video, and in this video you can see the liner up against the hole wall. The liner is internally pressurized with the excess head. You can see all these vugs on the side of the borehole wall. What you also can see here is a huge step at the bottom of this washout that actually is draped with the liner. And so, as you can see, the liner is like painted on the hole wall. This is a 6-inch diameter hole. You can see the seam tape here. It's about 1 inch in width. This big black object is just the back end of the light for the camera. In summary, the blank liner can actually seal the hole better than packers because it's so flexible and conforms so well with the hole wall. It seals the entire borehole. It's fully removable with minimum risk of entrapment, and it's used with several other measurements which I'll describe in a minute. Both the NAPL FLUTE and the FACT are emplaced as a covering of the blank liner. The NAPL FLUTE cover is a hydrophobic covering which wicks the NAPL upon contact. The FACT is an activated carbon felt strip which is sewn into the inside surface of the NAPL cover. The FACT wicks by diffusion the dissolve phase, which does not react with the NAPL FLUTE. Borehole water can be pumped from beneath the liner during the installation. This is what the NAPL FLUTE shows you when you take it out of the borehole. This stain right here is TCE. It's on the inside white surface of the NAPL cover. This is a coal tar stain, and this is a xylene stain that was mapped in the UK. The point is that all of these NAPL covers have identified the location of the NAPL. So in summary, the NAPL FLUTE will identify NAPL upon contact, can locate the mother lode of contamination. It's an easy addition to a sealing liner. It leaves the sealing liner available for other use, and it's complementary to the FACT. The FACT wicks the dissolve phase from fractures and the pore space. And the point is, and. It wicks both from fractures and the pore space. It's a continuous map throughout the entire borehole. It wicks the contamination by diffusion from the dissolve phase, and it's recovered by inverting the liner. It's a continuous replica of the contamination in pores and fractures. And the reason I point out that it's a continuous replica is it's very different from a groundwater sample collected at an interval, say with a packer. It's very different than a core sample, which measures the contamination only in the pore space of the rock. The FACT measures both. The entire strip should normally be analyzed, even if it's in very long segments. One method is to cut the strip in half lengthwise and to sample only long sections from the one half If you find a hot segment, the other half can be analyzed on the smaller scale. When combined with the NAPL FLUTe, the NAPL and the dissolve phase are both mapped throughout the entire borehole. These are some of the results of a FACT measurement. The FACT maps the dissolve phase both in the saturated zone and in the vadose zone. In the vadose zone, it maps primarily the vapors that are wicked up by the carbon. This is a comparison of 3 measurements with a geoprobe MIP to a FACT measurement. It turns out that the soil samples gave also exactly the same distribution. Is there any question about where the actual contamination is located? If this black line here is the FACT and it's drawing contamination from the formation, in this calculation, you can see that about 50% of the contamination is extracted from a depth of about 1.5 centimeters. And this occurs over a period of 2 weeks. So these various plots you see here are at later and later times. So in summary, the FACT is a continuous map of contamination and will not miss a fracture or a porous or permeable bed. The analysis is similar to a water sample in cost. The results are concentrations of species per gram of carbon. It addresses the basic question of where is the contamination. The entire felt strip should be analyzed if possible. A device for the continuous reading of the FACT is being developed by FLUTe. So now I'm going to talk about the transmissivity profile. It's fast and high resolution. It's performed with the same blank liner used for sealing the borehole, and which measures the liner descent rate. This photograph shows the liner being deployed off of the shipping reel through this machine which controls the tension and which measures the liner descent rate. This drawing shows that machine. Here's the roller that controls the tension on the liner. This is the encoder system that measures the descent rate. And as the liner descends, we also monitor with this transducer or bubbler the water level in the liner above the water table. In other words, the driving pressure. So as the liner propagates with the tension constant and with the driving pressure constant, the only thing that controls the liner descent rate then is how fast the water flows out of the borehole. So as the liner is propagating down the borehole, pushing the water into the fractures, when it passes a fracture, it seals it off. What that does is it reduces the transmissivity in the borehole beneath the liner. With that reduced transmissivity, the liner velocity must also be reduced. And so the liner velocity before it passes the fracture is greater than the liner velocity after it passes the fracture. The velocity difference between here and here, multiplied by the cross-section of the borehole, is the flow rate in that fracture before it was sealed. And so that velocity change not only locates the fracture, it also measures the flow capacity of that fracture. And that's true for every fracture passed by the liner. So the liner descent rate is controlled by the sealing of each flow path and the associated loss of transmissivity. It's also controlled by enlargements of the borehole. It would have been controlled by the tension on the liner and the excess head in the liner, except that both of those are constant. In a breakout or enlargement of the borehole, the liner slows and then accelerates as it exits. The reason the liner is traveling at one velocity here and a lower velocity through the enlargement is that the cross-section of the liner is larger. And so if you're driving at a constant flow rate, a larger piston would require a lower velocity. So the liner slows as it dilates, but when it passes into the borehole beyond the enlargement, it picks up its original velocity. So we apply a monotonic fit to the data that ignores temporary drops in velocity. You'll see that in the next view graphs. So here, this yellow curve is the actual velocity data going down the borehole. And so you can clearly see this velocity changes here as it seals off flowing sections in the borehole. The black fit is the monotonic fit, and you can see it travels right over these drops in velocity. So these are the enlargements in the borehole here at these differences between the yellow curve and the black curve. If we take this velocity curve right here, and every half second calculate the transmissivity of the interval traversed by the liner, you get this plot of very many data points. This is actually over 6,000 data points for the transmissivity in the borehole every half second as measured by the liner. If we integrate these individual transmissivity points from the bottom to the top of the borehole, we get this curve. Not surprisingly, it looks just like the velocity curve. What's nice about this curve, though, is that it's in units of transmissivity. And so this value right here is the transmissivity at the top of the borehole of the entire borehole. This value lower down is the transmissivity below 60 feet. And down here at 90-some feet is the transmissivity beneath 90 feet. And so if I take the difference between the transmissivity at this point and the transmissivity at that point, that is the transmissivity over that interval. If I integrated those same 6,000 data points over each 1 foot interval, I would get this plot. And this plot is the equivalent of 150 1-foot straddle-packer tests. It's pretty clear where the major flow zones are. But nobody does 150 1-foot straddle-packer tests. So the red curve is actually 1% of the total transmissivity, which is an estimate of the limit of resolution. These data points are above the red curve, they're reliable. If they're below the red curve, they may exist, but they're not reliable. So why do a transmissivity profile? Well, a big factor is it only takes 1 to 2 hours. If you were to do 5-foot interval straddle-packer tests of a 300-foot hole, it would take you 4 or 5 days. The total time that it took for doing this data set that we just looked at is less than 1 hour. We get a half-foot resolution of the flow paths. You just don't get that from flow meters or from packers. It provides flow capacity of each flow feature. There's no leakage, as with straddle packers. There's no entrapment of hole slough, as with straddle packers. The liner is then used to seal the borehole. So in summary, we map the flow zones in location and flow capacity, provides a continuous transmissivity profile for use with the reverse head profile, which I'll describe next. Very well suited for inclusion in modeling calculations. So now I'm going to be talking about the reverse head profile, how it's done, and why we do it. When the T-profile is finished, we let the transducer located at the bottom of the borehole equilibrate with the formation pressure at the bottom of the hole. The liner is tied off at the top of the borehole, and therefore it's stationary in the borehole. Then we invert the liner 1 increment. So the liner goes from this position to this position. We've moved it from this depth to that depth and over that interval. Then we let the transducer equilibrate again. We use the transmissivity plot to pick the intervals over which we're going to perform the head measurement. In this case, we use the actual transmissivity profile that you just saw before, and we selected these elevations to stop the liner. Each one of these intervals encompasses one of the high flow zones. So we went from here to here, we let the transducer equilibrate. We go from there to there and let the transducer equilibrate. And again, all the way up the borehole. Most people don't like to see all of these equations, but I want to describe this because of its simplicity. When we stop the liner at the bottom of the hole after the transmissivity profile and let it equilibrate, while it's equilibrating, we can write an equation for that equilibration process, which says the transmissivity times the pressure difference between the formation and the borehole pressure is the flow rate in and out of the hole. But when it's equilibrated, there's no flow. So at that point, the borehole pressure is equal to the formation pressure. If I invert the liner 1 increment, as I described, and I write an equation for that newly uncovered increment, it's the same equation, but now we have a new borehole equilibrium pressure. We still don't know the formation pressure in that interval, but the sum of the flow of the first interval and the second interval is equal to 0. And when I set those two flows equal to 0, I get this equation, and from that I can solve for the formation pressure in the newly uncovered interval. If I keep doing that, I get this very general equation for each newly uncovered interval, which is a function primarily of the new borehole equilibrium pressure, here, here, and here. They're all BHI. And the previously measured formation heads. You'll note that each time we sum these terms, we actually divide by the transmissivity profile of the newly uncovered interval. And so the result is dependent upon how well we have measured the transmissivity profile for each interval. So these are the results. This is the depth at which we stopped the liner each time. This is the transmissivity at each of those elevations from that graph I showed you earlier. And this column is the transmissivity difference between each of those elevations. In other words, this is the transmissivity of each interval. These transmissivity intervals, two of these in red, are extremely low compared to the other values. And as I pointed out earlier, this transmissivity value is in the denominator of the calculation of the formation head. And so if these values are not measured very, very well, one would expect that the formation head calculated would not be very reliable. This column is the equilibrium pressure measured each time we stopped. And so when we calculated finally the formation head of each newly uncovered interval, this is the result that we got. From these formation heads, we can actually calculate a water table for each interval. And from these formation water tables, we can actually calculate the flow into or out of the hole. Here are the actual formation heads calculated in this procedure. You can see at the shallower depths they're quite high, intermediate depths are intermediate, and at the lower depths they're low, except for this red point, which is way out here, and this red point, which isn't very different from that. So what can you tell from this plot of the head distribution? Well, for one thing, you have a generally downward gradient. You probably have an aquitard here between these 2 points and this point. This point is somewhat unreliable, so we should have some large error bars on it. And we also have a difference between this head and that head, but not so great as this difference. So, since this is an unreliable transmissivity used in the calculation, one should not pay particular heed to that. In fact, if you have a low transmissivity layer here, and you have a head above and a head below, it is almost certain that the head in that low transmissivity layer will lie between that point and that point. And so this red point should be probably somewhere halfway between that and that. As I said before, from the measured formation head values, I can actually calculate what the flow would be into or out of the borehole when the hole is open. In fact, the last measurement of equilibrium pressure is near the top of the hole. And so that last measurement has essentially the entire borehole unsealed. So if I take that unsealed value at equilibrium and use my formation heads measured, I can calculate the flow rate, in this case, into the borehole or out of the borehole. So in the upper part of the borehole, water's flowing into the borehole. In the lower part of the borehole, is flowing out of the borehole. And down here where we have very low transmissivities, it's actually hardly flowing at all. Since an important feature of this measurement method is that you allow the pressure to equilibrate when you stop the liner, one might ask, well, how long do I have to wait? Well, it turns out this is the actual data from one of those pauses in the measurement. And as you can see here, the pressure dropped severely when we moved the liner up. And then as it's equilibrating, it's approaching an asymptotic limit. We have a technique whereby using 3 data points equally spaced in time, we can calculate the asymptotic limit. And the point is, we don't have to wait until we get to perfect equilibrium, which in theory never occurs. And so what it means is, in 15 minutes, which is the time between here and here, we can either obtain the effective asymptote, or we can, in 10 minutes, between here and here, measure 3 data points and calculate the asymptote. So in principle, we only have to pause 10 minutes at each new elevation to make this measurement. And so in fact, in this test series, we only waited 2.5 hours to make the entire measurement of the formation head profile. So in summary, the reverse head profile maps a self-consistent profile in the formation. You can identify aquatards. It provides input for flow modeling, indicates the flow patterns in the open hole, and can identify artesian zones. You might ask, where do geophysical measurements come into this FLUTe sequence of measurements? Well, we very much like some geophysical measurements to be performed because a video provides supporting evidence of the flow features. A caliper shows potential influential features on data interpretation, and a flow meter is a nice check against the reverse head profile calculations. So, what do we need the rest of the typical geophysical measurements for? Some people like to see the temperature measurements, some people like to see the gamma logs, but frankly, with the information provided by the measurements that I just described, you may not need all of the other geophysical measurements. So now we're at the point where one should select the sampling intervals for a multi-level system. A multi-level system would be expected to measure water quality over time and to measure head over time. So which multi-level system? We would propose you would select one that seals the entire borehole with a continuous liner, not with packers, nor with a poured granular backfill of uncertain seal. One that draws directly from the formation. One that allows ample purging to draw from some distance from the borehole. One that draws through PVDF tubing. One that's easy to purge and sample, that doesn't aerate the samples. One that's fully removable for repair or abandonment. One that allows easy manual head measurements and also recording transducers. One that allows many sampling intervals, maybe 10 to 20 per borehole. One that's fully tested for continuity in the factory. One that's installed by experts without field fabrication in inclement weather. One that has a significant warranty. As you might expect, these conditions are met by the water FLUTe system. Well, this is a drawing of the water FLUTe system in place. It uses a continuous liner to seal the entire hole. Each sampling interval is defined by an exterior annular spacer. Behind that spacer is a port that connects with tubing that runs down the inside surface of the liner in a sleeve and comes up through a check valve and fills this, what we call a pump tube, to the water level in the formation. Transducers can be located at the bottom beneath this first check valve, or transducers can be located at the surface connected to each spacer through a separate tube. The pumping procedure is very simple. You connect a gas bottle through a regulator to a gauge, three-way valve, which is connected to the top of the pump tube. You turn the three-way valve after you've set the purge pressure, and the water is driven down in that tube. This valve closes, the water rises up through this tube to the surface. When you drop the pressure, the tube refills to the water level in the formation. Each of those strokes is called a purge stroke, and each purge stroke expels approximately 1 gallon of water. After the recommended 4 purge strokes, you lower this pressure to the sampling pressure. And then when you open this valve and you apply that pressure, you can't drive the water all the way out of the system. You only can drive it part way down. And now you have approximately 20 feet of water still in the pump tube. And so this air-water interface is 125 or more feet from your sample collection. The point is that this buffer prevents you aerating the sample. Since all of these pump tubes are of the same length, you can actually connect with a manifold to many of these pump tubes. In fact, for every spacer located at each discrete interval, there is a dedicated pumping system. And so we have a bundle of these pumps. And when we apply with a manifold the same pressure to each of these pump systems, all of the same length, we can simultaneously purge all the ports and sample all the ports. And so that simultaneous purge and sampling procedure greatly reduces the time it takes to collect groundwater samples. So what's our experience with the system? It's been in use for over 16 years. Installations have been done in boreholes from 2 to 18 inches to depths of 1,000 feet. However, installations in boreholes less than 3-inch diameter are usually custom orders. Many hundreds of systems are in place from Canada to Puerto Rico and as far as Denmark and Germany. Customers include Boeing, Shell, GE, ExxonMobil, EPA, NASA, Army Corps, and many other discerning customers. We have another water flute model. We call it a shallow water flute system. It uses the same sealing liner, spacers, and tubing and sleeves, and it's fully removable. The advantages are that it's less expensive, lighter weight, and installs like a blank liner. You can use peristaltic pumping, or we have a positive displacement pumped version which is available with fewer ports. With the shallow water flute system, we can provide 10 to 15 sampling intervals. It may be the least expensive multi-level system available. The difference between the shallow water flute system and our standard water flute system is that the water tables at all elevations for the shallow water flute system must be less than 25 feet below surface. Peristaltic pumping is normally used, but positive displacement pumping is available. If positive displacement pumping is used, half as many ports are available. Water tables are measured at each port with a vacuum water level meter. Air-coupled transducer systems can be directly connected to each sampling tube. The shallow water flute system costs approximately 50% less than our standard water flute system. The lower shipping weight also leads to a lower cost. So in summary, water flute systems use liners to seal the entire hole. They're very easy to sample, and the head measurements couldn't be more simple. They allow many sampling intervals. They can be used in ragged holes and in karst, where the liners seal wherever a seal is possible and without loss of sealants to solution channels. The borehole seal is more reliable than with poured granular annular seals or packers. They're fully removable. No heavy equipment is needed for field installation. They are frequently used in artesian conditions, and there's a wide variety of reliable head measurement methods available, from transducers to electric water level meters to vacuum water level meters to air-coupled water level meters. So finally, if you need precise vertical gradients or gradients between wells, we do have a precise gradient method. It doesn't use pressure transducers. In fact, a cell phone is sufficient for recording the head differences. You might notice that we haven't talked about packer testing. The reason is they leak, they can be trapped, require a long time with an open hole while it's cross-connecting, and they can provide erroneous data, so we haven't suggested packer testing. Some geophysical measurements I mentioned previously are useful in combination with FLUTe measurements. Those were the video, the heat pulse flow meter, and the caliper. The rest of the geophysical measurements I have not included because I'm not sure that they're necessary. I haven't talked about core measurements, such as chemical analysis of core. Core measurements require expensive boreholes, they don't measure fracture flow, and they don't measure NAPL in fractures, and so I've not suggested that core measurements ought to be made. Core measurements are of primary value for the geologic information. You can tell the difference between shales and chert and granites and so forth. Temperature measurements are typically of poor resolution, they're potentially misleading, and they're labor intensive. And I'm talking here even about temperature measurements made inside of liners. Distributed transducers with a blank liner have not been suggested here because I believe they're redundant, labor-intensive, and of limited time span. You can get pressure histories with either a reverse head profile or with a multi-level system. So who does the FLUTe installations? Blank liner installations are often done either by the customer, a driller, or by FLUTe. Blank liner removal with the transmissivity and head profile measurements are done by FLUTe. They're typically done in 1 day per borehole. Analysis of the fact requires subdivision by someone. Almost anyone can do that. And it has to be analyzed by a laboratory who does that sort of measurement. Water flute installations are done by FLUTe. It typically takes 1 day for 2 people to install a water flute. Sampling and head measurements are done by the customer. So the relative cost of the FLUTe approach is typically less than the traditional sequence. It usually provides better data. The best determination is just to ask for a quote and compare it to what you might otherwise be doing. There's minimal conflict with other activities and few delays in the plan. FLUTe systems are fully warrantable and removable, so the warranty is useful. I heard recently of an installation where the backfill materials were incorrectly placed. The only resolution was to drill the system out of the hole completely. If you have a problem with a FLUTe system, we just invert it out of the borehole and we fix it at our expense. No core hole is required, which makes it much less expensive. No packer testing is needed, and you have minimal geophysics required. And so those are great cost reductions typically. Frequently asked questions are on our website. And if you need more information, you can either go to our website or you can call us. If you need to discuss feasibility, just call me. If you need to know about scheduling, Ian Sharp, our field operations manager, addresses scheduling questions. If you need a quote, send us a request. If you need a procedure, you can contact me or you can go to our website. We deal with artesian conditions, karst, low-flow formations, fractured rock and sediments, shallow and deep, small and large diameter. We don't like squeezing clays or unstable boreholes, but we have methods even for those.